Module 1. Lecture C. Using built-ins effectively. By the end of this lecture, you will be able to evaluate when a built-in provides a clearer or faster solution than custom code, refactor simple loops and conditionals to use appropriate built-ins without sacrificing readability, and recognize common anti-patterns where built-ins are misused or unnecessarily wrapped. Readable built-in choices. Choosing obvious built-ins. When solving a problem in your program, start by using the most obvious built-in function that matches the task. These functions have clear names and well-known behavior, so other programmers can quickly understand your intent. For example, using a built-in to find the maximum value is clearer and less error-prone than writing your own loop. This approach improves readability and maintainability, especially when working in a team with people of different experience levels. Using built-in functions can improve performance without requiring low-level optimization. These tools are usually implemented in efficient native code, so tasks like aggregating values or searching through collections run faster than many custom solutions. The performance gains may be small on tiny inputs, but become important with large data sets, such as in web applications or data analysis. By selecting a built-in that clearly matches your goal, you benefit from a well-tested, accurate, and efficient component, and can focus on the overall logic of your program instead of micro-optimizations. When choosing built-in features in a programming language, favor those that are clear and familiar to most readers. Use constructs that are common in idiomatic code, and avoid obscure functions or combinations that hide the main idea and hurt readability. A simple test is to explain the code out loud and see if your explanation matches the built-in's name and behavior. With practice, you will learn which built-ins are obvious and when it is better to write custom logic instead. Python code. Choosing obvious built-ins. When writing code, prefer obvious built-in tools to keep your solutions clear and readable. Instead of manually writing loops to find a maximum or compute a total, use built-in functions that do this directly. These built-ins quickly communicate your intent to other readers and reduce unnecessary complexity in your programs. Imagine a list of numbers that represent how many miles delivery trucks drive each day. We will use this list to show how built-in functions can quickly perform common tasks. These tasks include finding the largest value in the list and calculating the total distance driven. Using these built-in tools is simpler and more efficient than writing manual loops to do the same work. To find the largest number in a list, you first store the value of the first element as your current largest. Then, you go through the remaining elements one by one, and each time you see a value that is greater than your current largest, you replace it with this new value. After you have checked every element in the list, the stored value will be the largest number in the entire list. This line prints the largest value found by a manual loop through the list of numbers. It shows the final result that was stored after comparing each element to track the maximum. This illustrates how you can determine the maximum value yourself by checking each item in turn. However, in practice, using a built-in function to find the maximum is usually more efficient and easier to read. We use the max function to quickly find the largest number in a list called numbers. This built-in function automatically identifies the maximum value, so the code stays short and easy to read. After it finds the largest number, we print that value along with a message explaining that we used the max function to get the result. To manually find the total of a list of numbers, you start with a running total set to 0. Then you go through each number in the list one by one. For each number, you add it to the running total. By the time you reach the end of the list, this running total holds the sum of all the numbers. This code prints the total miles driven by adding up daily values stored in a list using a manual loop. The loop keeps a running total in a variable that accumulates each day's miles. This approach is then compared with using built-in functions that perform the same calculation more directly. The comparison shows that built-in tools can make the code shorter than the programmer's intent, easier to understand. We use the sum function to quickly add all the numbers in a list and get their total. After computing this total, we print it along with a note that it was calculated using the built-in sum function. This demonstrates how built-in tools provide a clear and efficient way to perform common operations like adding a list of numbers. This line prints a message that emphasizes the value of using Python's built-in functions. These built-in tools make the purpose of your code clearer and are usually faster than writing your own versions. Because they are optimized for both performance and readability, they are preferred whenever they can replace manual implementations. This script shows why using built-in functions can make code clearer and more efficient. It first finds the largest daily mileage with a manual loop, then repeats the task with the built-in maximum function, which is shorter and expresses the goal more directly. It does the same for computing total miles, comparing a manual loop with the built-in sum function. In both cases, the results match, but the built-in versions are simpler to read and often run faster behind the scenes. Simplifying nested built-ins. When you start using built-in functions heavily, it can be tempting to chain many of them together into one complex expression. But this often makes the code harder to understand, especially for beginners. The real challenge is noticing when this complexity hides the main idea of the code. In situations like data processing, where you filter, transform, and aggregate records, putting everything into one nested expression may look efficient, but is difficult for others to read and change. Instead, aim to use built-in functions in a way that keeps each step clear, separate, and easy to follow. When working with complex, nested expressions, it helps to break them into a few clear steps with names instead of stacking many built-in operations together. In tasks like cleaning data or processing logs, adding a couple of extra lines is usually worth it to avoid confusion later. You might, for example, first select the subset of data, then apply your transformations, and finally summarize the result. This step-by-step structure makes your intent easier to understand. Verify, log, and adjust when requirements change without sacrificing performance. When simplifying nested built-in operations, you need to balance performance with readability. In performance-critical areas like real-time analytics or scientific computing, some nesting can be worthwhile to reduce overhead. It is acceptable if the nested expression stays understandable, especially with a clear variable name or a brief comment. However, if you or others struggle to see what data is being processed, that is a strong signal to refactor the code for clarity. Python code, simplifying nested built-ins. Deeply nesting built-in functions can make code hard to read and understand, especially when doing tasks like filtering data and computing an average. Instead of stacking many operations inside one long expression, it is clearer to break the work into small, named steps. For example, first filter the data, then store the result, then compute the average in a separate step. This stepwise style makes the logic easier to follow, debug, and modify, while still performing the same simple data filtering and averaging as the nested version. We begin with a simple list of daily temperatures in Fahrenheit for 1 week. This list serves as our basic dataset for demonstrating how to filter and average values. Because the temperatures are stored in a straightforward list, it is easy to apply operations such as filtering out certain readings or sorting them before calculating an average. We take a list of Fahrenheit temperatures and first filter it to keep only values of 70 degrees or higher. We then sort these hotter temperatures in ascending order and add them together. Next, we divide this total by how many hot temperatures there are to get the average temperature for the hot days. All of these steps are combined into one deeply nested expression, which can make the code harder to read and understand quickly. We use a list comprehension to filter the Fahrenheit temperatures and keep only the hot days. It goes through each temperature and checks whether it is at least 70 degrees. If the condition is met, that temperature is added to a new list called hot days. This clearly separates the filtering step from other work in the code, which makes the program easier to read and maintain. We take the list of hot days, meaning the temperatures that meet our criteria, and sort them from lowest to highest. This sorting step organizes the data so it is easier to work with. Once ordered, we can more clearly perform tasks like averaging and other analysis. Overall, sorting helps keep our results clear, logical, and easy to interpret. To find the average temperature of the hot days, add together all the temperatures in the sorted list of hot days. Then divide that total by how many temperatures are in the list. The result is the average temperature for the days that were classified as hot. The code calculates and prints the average of all temperatures that are 70 degrees or higher, using a single nested expression. It filters out lower temperatures, sorts and sums the remaining values, and then divides by how many values are left. The printed result can then be compared with the average produced by the stepwise approach to confirm that both methods give the same value. We compute the average temperature for hot days using a stepwise approach. First, we keep only temperatures that are 70 degrees or higher. Then we sort these values, and finally, we calculate their average. Organizing the work into these clear, named steps makes the process easier to read and understand. The code prints a message that shows the list of hot days after filtering and sorting the temperature data. It first keeps only temperatures that are at least 70 degrees Fahrenheit. Then, sorts these values in ascending order. Displaying this sorted list of hot days allows you to check that the filtering and sorting steps worked as intended and that the data processing logic is correct. This script compares two ways to compute the average temperature on hot days, defined as days above 70 degrees Fahrenheit, to show how deeply nested built-in functions affect readability. One version uses a single complex expression that filters, sorts, and sums the temperatures, then divides by how many hot days there are. The other version performs the same steps in a clearer sequence, first filtering the temperatures, then sorting them, and finally calculating the average. Both approaches produce the same average temperature and print the sorted list of hot days, confirming that the simpler, step-by-step style is easier to read without changing the result. Clear versus concise. When choosing whether to use a built-in feature, you are balancing clarity against conciseness. Short, compact code can look elegant, but it is not helpful if others, or your future self, must mentally unpack or test it just to see what it does. Good code makes its purpose obvious at a glance, without needing to reconstruct the logic step by step. So, use built-ins not just to shorten code, but only when they also make the intent immediately clear to someone familiar with the language. When writing code to process data, such as survey responses, it is important to balance clarity and conciseness. Overly compact code that chains many built-in functions can hide the logic and make it harder to understand. A better approach is to use a single built-in for the main task and keep the rest of the code simple and explicit. This is especially valuable in areas like data analysis, web applications, and financial systems, where clear code improves safety and maintainability. Concise code is helpful only when it does not obscure the underlying idea. Built-in functions are like shared vocabulary for your team, and using familiar ones can make code clearer and shorter because everyone understands the pattern. But stacking many less familiar built-ins or depending on subtle behavior can confuse people and introduce bugs, especially when requirements change. In high-stakes systems like medical records, a clever one-line solution may look impressive but can be risky. Aim for a balance where built-ins simplify your code without turning it into a puzzle. Python code, clear versus concise. Show how to use built-in features in both a clear and a concise way, and compare a dense one-line version with a more readable multi-step version. Emphasize that while short, compact code can look impressive, it is often harder to understand and maintain. Make it clear that, in practice, choosing clarity over extreme concision usually leads to better, more reliable code and easier collaboration. We begin by setting up a list of responses made up of the strings yes, no, yes, maybe, yes, and no. This list simply stores a small collection of possible answers. It is prepared so that later in the code, we can analyze these responses, such as counting how many times each type of answer appears or checking for specific patterns. The key idea is that we now have a structured set of response data ready for further processing. We start by defining the category we want to count in the list of responses. By setting a variable equal to the word yes, we indicate that we are interested in how many responses are yes. This choice lets us later use that variable to filter the list and count only the responses that match this category. In short, defining this category up front makes it easy to focus on and count just the yes answers in the data. This line of code counts how many responses belong to a specific category in a compact way. It uses a generator expression inside a sum operation, which goes through each answer in the list of responses. For every answer that matches the target category, it produces a value of 1. The sum operation then adds these ones together to give the total number of matching responses. We begin by using a list comprehension to filter the responses. It goes through each answer in the list and checks whether it matches the category we want to count, which is stored in a separate variable. Only the answers that match this category are collected into a new list called filtered responses. This approach clearly separates the filtering step from the counting step, making the overall logic easier to understand. We find how many responses match the category yes by first creating a filtered list of only those responses, then measuring the length of that list. The length tells us the total count of matching responses. Separating the filtering from the counting keeps the logic clear and easy to understand. The code prints the result of the concise counting method, showing that the count it produces equals a specific number stored in the concise count variable. It also indicates which category is being counted, using the value stored in the category variable. This output is used to confirm that the concise method correctly counts how many times the chosen category appears in the list of responses. This line displays the final count result, showing how many times the chosen category appears in the list. It reports both the number of occurrences and the category being counted. This makes the outcome of the filtering and counting process clear and easy to interpret. This script compares a concise and a clear way to count how many times the word yes appears in a list of responses. The concise version uses a single expression to both filter and count the matches. The clearer version separates these steps, first selecting the yes responses and then counting them. Both approaches produce the same result, showing that 3 yes responses are found. This illustrates that a more readable method can be just as effective as a shorter, more compact one. Efficient built-in usage. Loop performance comparison. When comparing a handwritten loop to a built-in operation, focus on how clearly each one expresses your intent and how much work it creates for the interpreter. A manual loop may be correct, but harder to read than a concise built-in that directly states what you want, such as finding the largest value in a list or counting certain survey responses. Using the right built-in can improve performance and, just as importantly, reduce mental effort for future maintainers. They can understand the operation at a glance instead of tracing through detailed loop logic. Built-in functions are usually faster than loops you write yourself because they are implemented in low-level, highly optimized code. A manual loop in a high-level language has to repeatedly interpret each step and perform lookups, which adds overhead. In contrast, built-ins minimize this overhead, use memory more efficiently, and create fewer temporary objects. As a result, tasks like aggregating transactions or filtering logs run more quickly and use fewer resources when done with built-in operations rather than custom loops. When choosing between loops and built-in functions, balance performance with readability and context. In small scripts, speed differences are often minor, so favor whatever is easiest to understand. In high-demand settings like web services or data science workloads, repeated inefficient loops can slow things down, making built-in operations a better choice. Build an intuition for when a loop is just recreating what a built-in already does, and when refactoring. Consider both clarity and speed. If a built-in makes the code faster and easier to read, it is usually a smart replacement for the loop. Python code loop performance comparison. We can compare manual loops with built-in functions by looking at how they both compute the same result on simple numbers. A manual loop processes each value step by step, while a built-in function performs the same operations in a single, higher-level call. Both approaches can produce identical outputs, but built-in functions are often faster because they are optimized behind the scenes. They also tend to make the code easier to read and understand, since the intent is clearer and there is less low-level detail to follow. The script starts by importing the timeit module, which is used to measure how long small pieces of code take to run. This tool is helpful for performance testing because it lets us compare the speed of different coding approaches. In this case, timeit is used to measure and compare the execution time of manual loops versus built-in functions, giving a clear sense of which method is faster. We create a list called miles per day that records how many miles were driven on each day of a month, with one value for each of the 30 days. This list serves as a simple data set we can use to explore different ways of finding the largest value. Using it, we can compare a step-by-step manual method with a built-in method and see how both approaches arrive at the same maximum miles driven in a day. The manual max function finds the largest number in a list by starting with the first element as the current maximum, then scanning through the rest of the list. For each number, it checks whether that number is greater than the current maximum. If it is, the function updates the current maximum to this new value. After it has checked all the numbers, it returns the final maximum as the largest value in the list. The function, called built-in max, is used to find the largest value in a list of numbers. It accepts one input, which is the list of values, and then relies on Python's own max function to determine which number is greatest. By using this built-in capability, the function stays simple, efficient, and avoids manually looping through the list to search for the maximum. We first find the maximum miles driven in a day using a manual method that iterates through the list of values. Then we use the built-in maximum function to get the largest value directly from the same list. After we have both results, we print the maximum from the manual method and then the maximum from the built-in method. Seeing that both values match confirms that our manual implementation is correct. We use the timeit library to measure how long each method takes to run. First, we time the manual loop by repeatedly calling the custom maximum function on the list of miles per day many times to get a reliable average. Then, we repeat the same timing process for the built-in maximum function using the same list and number of repetitions. By timing both approaches under the same conditions, we can directly compare their performance. We measure how long it takes to find the maximum value using a manual loop, then round and print that time. We do the same for the built-in maximum function, again rounding and printing the result. Finally, we compare the two times and print whether the built-in function is faster than the manual loop. This example compares finding the maximum daily miles driven using a manual loop versus a built-in function. Both methods produce the same maximum value, so they are equally correct. However, when each approach is repeated many times, the built-in function runs noticeably faster than the manual loop. This shows that using optimized built-in functions in Python can improve both clarity and performance compared with writing your own loops. Efficient sum and max. When working with collections of numbers, tasks like adding all the values or finding the largest one are so common that they should be written in a clear and efficient way. Writing manual loops for these operations can make the code longer and obscure its real purpose. Instead, using built-in functions lets you state directly what you want to do, such as computing total sales or finding the best month. This makes the code easier to read, understand, and maintain. Refactoring loops that compute sums or maximum values into built-in functions is not just about shorter code. It better matches how you think about the problem. Instead of mentally tracing each step in a loop, built-in operations make the goal immediately clear, such as finding total energy use or a peak value in sensor data. This clarity lets you focus on issues like data quality or outliers rather than low-level iteration details. As your programs grow more complex, this emphasis on clear intent helps keep the code easier to read and understand. When using built-in functions like sum and max, focus on keeping your code readable, especially with complex data structures. For simple lists, this is easy, but with things like customer records or time-stamped events, make sure it is clear how you turn each item into a number. If you are computing total revenue or the largest order, avoid tangled expressions and show the numeric extraction step plainly. Let the built-in functions handle the aggregation, while your code clearly shows what is being summed or compared, so the link to the real-world problem stays obvious. Python code, efficient sum and max. We will compare using explicit loops with using built-in functions to work with sales data. First, we will show how to sum sales using a loop. Then contrast that with using a built-in sum function. Next, we will find the maximum sale using a loop, and then with a built-in maximum function. Throughout, we will focus on keeping the data transformations clear and readable while taking advantage of these concise built-in tools. We begin by creating a list that holds monthly sales in dollars. This list has 7 values, and each value represents the revenue for 1 month. Its main purpose is to store the sales data in one place, so we can later calculate the total revenue and find the month with the highest revenue. We begin by setting a running total of sales to 0, which will store the cumulative revenue. Then we go through each value in the list of monthly sales and add it to this running total. By processing the sales one by one, the loop clearly shows how the overall revenue is built up step by step from the individual monthly amounts. We can compute the total revenue by using Python's built-in sum function on the list of monthly sales. This function automatically adds all the values in the list and returns their total. It performs the same calculation as a manual loop, but does it more directly. As a result, the code is shorter, clearer, and easier to read while producing the same total revenue. To find the month with the highest revenue using a loop, first treat the sales from the first month as the current maximum. Then move through the remaining months one by one, and each time you see a sales value that is larger than the current maximum, replace the maximum with this new value. Continue this process until you have checked all months. The final maximum value you are left with is the highest monthly sales figure. To find the month with the highest revenue, you can use Python's built-in maximum function on the list of monthly sales. This function quickly scans all the values and returns the largest one. The result represents the best month in terms of sales. This method is both concise and efficient because it relies on Python's optimized internal processing. We first calculate and print total revenue using a loop to manually add each month's sales. Then repeat the calculation using the built-in sum function, which produces the same result with less code. We do a similar comparison for maximum monthly revenue, first finding it with a loop that checks each month, and then using the built-in max function to get the same value more directly. Together, these steps show that built-in functions can make code shorter, clearer, and more efficient than explicit loops, while giving identical results. This script compares two ways to calculate total revenue and the highest monthly sale from a list of sales figures. It first uses manual loops to add up all the sales and track the maximum value. It then repeats the task using Python's built-in sum and max functions, which are shorter and easier to read. Both approaches produce the same results: a total revenue of $6,330 and a highest monthly sale of $1,750. The example emphasizes how built-in functions can make code more efficient and readable than manual loops. Avoiding unnecessary list copies. When using built-in functions, try to avoid creating unnecessary copies of lists because they waste time and memory, especially with large datasets. Chaining many operations can look concise, but it often causes the data to be scanned and copied multiple times, which slows your program down. Instead, aim to process the data in a single pass by using tools that work in place or evaluate lazily. This approach keeps your code readable while reducing extra work and resource use. When working with lists, try to avoid creating unnecessary copies of your data. If you filter, transform, and then summarize using separate loops, you build multiple full lists in memory, which wastes time and space. Instead, prefer tools that operate directly on iterables or combine steps into a single pass, such as using one comprehension. Whenever you can, pass iterators straight into built-in functions so they can work with lighter weight representations. Only materialize a full list when you truly need random access to the data. Developers often waste time and memory by making unnecessary copies of lists, such as wrapping built-in functions in extra loops or conditionals that do not change the data. This can happen in data cleaning, where a list is copied just to remove invalid entries, or in user interfaces, where a list is copied before sorting, even though the original is not needed. The key is to decide whether you truly need to preserve the original data. If you do not, avoid redundant copies so your code stays faster and more efficient. Python code: avoiding unnecessary list copies. This lesson explains why creating unnecessary copies of lists wastes both memory and processing time. It contrasts a list-based approach, where all data is stored in memory at once, with a generator-based approach that produces items on demand. You will see how generators can be more efficient, especially for large datasets. The lesson also shows how to use built-in functions directly, without first turning everything into a list, so your code stays faster and more memory efficient. The script starts by importing the time module, which provides tools for working with time in Python. Here, it is used to record when specific operations begin and end. By comparing these timestamps, we can calculate how long each part of the code takes to run. This timing information is then used to compare the performance and efficiency of different methods in the script. We create a large list to simulate daily sales amounts in dollars, containing about 500,000 entries. Each value is generated by taking its position in the list, finding the remainder when divided by 200, and then adding 10. This produces a repeating sequence of sales figures ranging from $10 to $209. The result is a diverse set of sales amounts that can be used for further analysis. We set a threshold of $150 to identify high-value sales in a list of daily sales amounts. Any sale above this threshold is treated as a significant transaction. Using this cutoff lets us filter the data so we can focus only on the more important revenue-generating sales. We begin by recording the current time with a performance counter so we can measure how long an inefficient method takes. Then we use a list comprehension to scan through all sales and select only those above a given threshold, storing them in a new high sales list. This method is inefficient because it builds a complete intermediate list in memory, which can be expensive in both time and space when working with a large sales dataset. We now convert the high sales into discounted amounts by creating a new list where each sale is multiplied by 0.9. This multiplication applies a 10% discount to every value. The result is a list that contains the discounted versions of all the high sales amounts. We first find the total of the discounted high sales by adding together all the values in the discounted sales list, which gives the overall amount after each sale has been reduced by the discount. Then, we measure how long the inefficient method takes by recording the start time, recording the time when it finishes, and subtracting the two. This time difference tells us the duration of the inefficient process and helps us evaluate its performance. We begin by recording the current time so we can measure how long the efficient method takes. Next, we use a generator expression to scan through the large list of sales and select only the amounts that are greater than the given threshold. Because this generator produces values on the fly instead of building a separate list, it avoids creating an intermediate data structure and saves memory while still filtering the sales data effectively. In this step, we use a generator expression to apply a 10% discount to each sale amount that has already been filtered to include only values above a certain threshold. The generator takes each qualifying sale and multiplies it by 0.9 to reduce the price. By using a generator instead of a list comprehension, we avoid creating an extra list in memory. This makes the operation more efficient in both memory usage and execution time. We compute the total discounted sales by directly summing the values from a generator, which avoids creating an extra list and saves memory. To evaluate how efficient this method is, we record the start time, run the calculation, then subtract the start time from the current time using a performance counter. This difference gives the elapsed time for the efficient approach. We can then compare this timing with that of the less efficient method to see the performance improvement. The code calculates and prints the total discounted sales for both the inefficient and efficient approaches. It first shows the total from the inefficient method, rounded to 2 decimal places. Then shows the total from the efficient method, also rounded. This side-by-side output makes it easy to compare the results of the 2 approaches. We measure how long the inefficient approach takes and round the result to 4 decimal places so the timing is easy to read. Then we do the same for the efficient approach. Comparing these 2 rounded times shows how much faster the efficient method is. This highlights the performance benefit of using generators instead of lists. This script compares inefficient and efficient ways to process large lists in Python. It first builds a large list of sales amounts, then shows an inefficient method that filters high-value sales and applies discounts using separate steps that create extra lists in memory. It then shows a more efficient method that uses generator expressions to perform the same filtering and discounting without creating intermediate lists. Both methods produce the same total discounted sales, but the generator-based approach runs faster and uses less memory, demonstrating why generators are better for large data processing. Built-in anti-patterns. Rewriting core functions. Programmers sometimes rewrite basic operations that the language already provides, such as searching or combining data, to show they understand control flow. However, this often produces slower, more error-prone code that is harder for others to read. For example, manually finding the maximum value in a list can hide the intent, while a built-in function makes it clear and reliable. Writing such code can be useful for learning, but in production, it is better to rely on well-tested, familiar language features. Writing your own versions of basic functions often introduces subtle bugs, especially with edge cases like empty inputs or unusual data types. Built-in operations are usually faster, more reliable, and thoroughly tested, while custom code written quickly does not get the same level of scrutiny. These homemade functions also make programs harder to read and maintain because future developers must decode unfamiliar logic instead of recognizing standard tools. In settings like research labs, this can confuse new team members, cause errors in tasks such as summing or filtering data, and ultimately distort results and waste effort. Instead of rewriting features the language already provides, learn to trust and use its built-in functions. When you start writing a loop for a common task like counting or checking conditions, pause and ask whether a built-in already does this more efficiently. In real projects, such as web or financial applications, relying on these well-tested tools usually improves performance and reduces errors. It also makes your code easier for teammates to read, understand, and maintain. With experience, you will better recognize when you truly need custom logic and when it only adds unnecessary complexity. Python code, rewriting core functions. Show how rewriting core built-in functions is usually unnecessary and can hurt performance. Compare slower custom loops with the clearer and more reliable built-in operations they try to replace. Emphasize that learners should recognize when they are reinventing the wheel and instead rely on trusted built-in tools. The goal is to build the habit of removing redundant custom code in favor of simpler, standard solutions. This function finds the largest number in a list by manually scanning through the values instead of using Python's built-in tools. It begins by treating the first number as the current maximum, then compares each remaining number to this value. Whenever it encounters a larger number, it updates the current maximum. After checking all the numbers, it returns the largest one found. This process imitates what the built-in maximum function does, but in a more verbose and less efficient way. A custom sum function calculates the total of a list of numbers by keeping a running total. It begins with the total set to 0, then loops through each number in the list. For every number, it adds that value to the running total. After all numbers have been processed, it returns the final total, which is the sum of the list. This simply recreates what the built-in sum function already does, without adding any extra advantages. We create a list that stores several numbers, each representing a daily temperature measured in degrees Fahrenheit. This list serves as sample data for the rest of the script. It will be used to compare the results of custom functions with Python's built-in tools for finding the maximum value and the total sum of the temperatures. We first use a custom function that goes through the list of temperatures one by one to find the highest value, showing how a manual maximum search works. Then we apply another custom function that adds each temperature to a running total to compute the overall sum. Together, these calculations illustrate how our own implementations operate and set us up to compare their results with those from built-in functions. In this example, we rely on Python's built-in tools to work with a list of temperatures efficiently. We use the max function to quickly find the highest temperature, taking advantage of Python's optimized internals. We then use the sum function to add all the temperatures together. These built-in functions are preferred because they are clear, concise, and avoid writing manual loops to perform the same tasks. The code first shows the result of a custom maximum function that finds the highest temperature using a manual loop, and then shows the result of the built-in maximum function, which produces the same value more efficiently. This side-by-side comparison makes it clear that the custom version simply repeats what the built-in function already does. It does not add new features or improvements, so using the built-in function is the better choice. The code first shows the total temperature calculated by a custom function that adds each value one by one. It then shows the total from the built-in sum function using the same data. Comparing these results demonstrates that built-in functions can perform the same task with much less code. It also emphasizes that built-in tools are usually more efficient than writing your own manual loops. The final line of the script prints a reminder that programmers should use built-in functions, such as those that find a maximum or compute a sum, instead of writing their own loops to do the same work. This emphasizes that built-in tools are usually more efficient, clearer to read, and thoroughly tested. Relying on them leads to simpler, more reliable code than manually re-implementing their behavior. This script shows why it is usually a bad idea to rewrite Python's built-in functions for tasks like finding a maximum or computing a sum. It uses a list of temperatures and compares custom functions that manually loop through the data with the built-in versions. Both approaches produce the same results, but the built-in functions are shorter, clearer, and generally faster. The main takeaway is that you should rely on Python's built-in tools instead of reinventing them yourself. Overusing print wrappers. In programming, a common problem is creating custom output functions that do little more than what the built-in tools already provide. Developers may intend to centralize formatting or logging, but they often end up with several similar wrappers for debugging, errors, and other messages. This makes simple tasks like showing a message more complicated because you must learn what each wrapper does and what side effects it might have. As a result, the code becomes less clear and harder to follow, especially for new team members or when you return to it later. Custom output wrappers that change how results are displayed can cause subtle problems, such as hiding errors or unexpectedly changing formatting. In data analysis, this might lead to truncated values and misinterpretation. While in web applications, it can make user messages confusing, for example, by adding timestamps. These wrappers blur the distinction between simple display and logging, which makes the system harder to understand and maintain. As a result, small changes in the wrapper can have unexpected effects across the entire code base. Use custom output functions only when they provide capabilities that the standard outputs do not, and keep their purpose narrow and clearly documented. A good example is a dedicated logging utility that formats messages, adds metadata, and sends them to files or monitoring tools separate from anything shown to users. Avoid writing thin wrappers that simply rename built-in functions or add small visual tweaks, because they usually add complexity without real benefit. Always ask whether a custom wrapper truly improves clarity or functionality, or whether it just obscures the direct use of built-ins. By removing unnecessary layers, you keep your code clearer, more transparent, and easier for others to understand. Python code: overusing print wrappers. This section explains why adding thin wrapper functions around basic print statements is usually unnecessary and can make code harder to understand. It shows that these wrappers often do not add any real behavior or value, but instead create extra layers that obscure what is actually being printed. By comparing output produced through wrapper functions with output produced by calling print directly, it highlights that direct printing is clearer, simpler, and easier to follow. The main point is to favor straightforward print calls over minimal wrappers that only add confusion. We define a function called debugMessage that takes one input named text and simply passes it to the print function. This means the function does not add any new behavior or logic. It is just a thin wrapper around print. The example is used to show that such wrapper functions are often unnecessary when they do nothing beyond calling an existing function. In this example, we define a function called errorMessage that takes one input called text and simply calls the print function with that input. The wrapper does not change the behavior or add any new features. It just forwards the text to print. This shows how creating such wrapper functions can introduce extra complexity without offering any real advantage. The code starts by announcing that it is using wrapper functions for simple status messages, setting the context for what follows. It then calls a debugMessage function with a description of loading data from a warehouse in Texas, and an errorMessage function with a description of a failure when loading data from a backup drive. Both wrapper functions simply print the messages they receive, but understanding the code requires knowing what these functions do. This adds an extra layer of abstraction that may be unnecessary for such straightforward printing tasks. A code uses simple print statements to clearly show what it is doing. It first prints a message that it is loading data from a warehouse in Texas. Then, it prints another message indicating that loading data from a backup drive has failed. These direct print calls keep the code easy to read and understand without relying on extra helper functions. This script shows that creating thin wrapper functions around a print statement is usually unnecessary. It defines separate functions for debugging and error messages that simply pass their input straight to print without adding any new behavior. When the script runs, it prints messages both through these wrappers and by calling print directly, producing the same result. The example illustrates that using print on its own is clearer and avoids extra complexity. The main lesson is that unless a wrapper function adds meaningful functionality, it is better to use direct print calls for more readable and maintainable code. Shadowing built-ins. Shadowing built-in functionality happens when a developer gives a variable, function, or module the same name as a language feature, which hides the original behavior. After this, any use of that name refers to the new definition instead of the built-in one. This often leads to confusing errors and bugs that are difficult to track down, especially for others who expect the standard behavior. In larger projects, this can damage trust because it disrupts the expected meaning of common names. Reusing built-in names for your own variables or functions creates confusion because people expect those names to behave in their standard way. When a familiar name is shadowed locally, readers must constantly wonder whether it is the usual feature or a custom one. This slows down understanding, increases mistakes, and makes error messages harder to interpret. The problem is especially serious in areas like data science or web applications, where hiding a standard feature can make debugging much more difficult. Using your own variables or functions with the same names as built-in features of a language can make your code fragile and cause it to fail in different environments. A script might seem fine on its own, but break when combined with other modules that depend on the original built-in behavior. This can turn a harmless teaching example into a serious problem in real projects, where libraries and tools expect those built-ins to exist. To prevent these issues, choose clear, descriptive names that are specific to your problem domain and avoid reusing names from the language's core features so your code remains stable and easy to understand. Python code, shadowing built-ins. Show how using a variable name that matches a built-in function can cause confusing and unexpected behavior. Give a bad example where a variable is named the same as the built-in function that adds up values, which hides the original function and makes it unusable. Then correct this by demonstrating a version that uses clearer, safer variable names so the built-in function remains available and the code behaves as intended. We create a list of measurements in inches with the values 10, 20, 30, and 40, and then use the standard sum function to add them together. The program prints the total along with a message explaining that this is the result from the real built-in sum function. This simple example shows the normal, expected behavior of the sum function when nothing has changed or overridden it. Assigning the value 100 to something named sum is a problem because it uses the same name as the built-in sum function and hides it. After this assignment, when you try to use sum, you no longer have access to the original function. Instead, it just behaves like a regular value equal to 100. This shows how reusing a built-in name can accidentally disable important built-in behavior. In this example, a variable is given the same name as a built-in function that normally adds up values. The code then tries to use that name as if it were still the function and passes a list of numbers to it. Because the name now refers to an integer instead of a function, this attempt causes a type error since an integer cannot be called. A try except block catches the error and prints a message explaining what went wrong. This illustrates the problem of shadowing built-in functions by reusing their names for variables. To fix the problem of accidentally replacing the built-in sum function, you remove the local variable that uses the same name. Deleting this variable stops it from hiding the original function. Once it is removed, you can call the built-in sum function again with a list of numbers, and it will return the correct result. This shows that the built-in behavior has been successfully restored. This script shows why you should avoid using the same names as Python's built-in functions. It first uses the built-in sum function correctly to add a list of numbers. Then it creates a variable with the same name, which replaces the function and causes a type error when you try to use sum again. Deleting this variable restores the original function so the calculation works as expected. The example emphasizes that choosing variable names carefully helps prevent these kinds of conflicts and errors. In this lecture, you learn to evaluate when a built-in provides a clearer or faster solution than custom code, refactor simple loops and conditionals to use appropriate built-ins without sacrificing readability, and recognize common anti-patterns where built-ins are misused or unnecessarily wrapped. In the next module, Module 2, we will go over core scalar types. Thank you for your attention. See you all in the next lecture.